Torch, quantizepertensor. Description. Inputs. Tensor. The tensor to be quantized. It can be of any data type supported by p-torch. Scale. The scale factor used for quantization. It must be a positive float. 0. The 0 point used for quantization. It must be an integer. Quantized tensor. A tensor of the same shape as the input tensor, but with quantized values. The data type of the quantized tensor will be torch, quint8 or torch, quint8 depending on the input. Tensor's data type. Steps. The input tensor is divided by the scale factor. The result is rounded to the nearest integer. The 0 point is added to the rounded value. The resulting value is stored in the quantized tensor. Challenge 1. If the scale factor is too small, the quantized values may not be able to represent the full range of values in the input tensor. This can lead to loss of precision. Sample use case that resulted in challenge 1. If the input tensor has values ranging from 0 to 100, and the scale factor is set to 0.1, the quantized values will only be able to represent values in the range of 0 to 10. Fixes to challenge 1. Increase the scale factor to a value that is large enough to represent the full range of values in the input tensor. Challenge 2. If the 0 point is not chosen carefully, it can lead to bias in the quantized values. Sample use case that resulted in challenge 2. If the 0 point is set to 128, all quantized values will be shifted by 128. This can lead to a bias in the quantized values. Fixes to challenge 2. Choose a 0 point that is appropriate for the input tensor's data type and range. Challenge 3. If the input tensor is not properly normalized, quantization can lead to significant loss of precision. Sample use case that resulted in challenge 3. If the input tensor has values ranging from -100 to 100, but the scale factor is set to 1, the quantized values will only be able to represent values in the range of -128 to 127. Fixes to challenge 3. Normalize the input tensor before quantization to ensure that the values are in a range that can be accurately represented by the quantized data type. Torch, quantize per channel. Description. This function quantizes a tensor per channel, meaning that each channel of the tensor will be quantized with its own scale and 0 point. This is useful for optimizing performance and memory usage in models that require a wide range of values across different channels. Inputs. Tensor. The tensor to be quantized. This tensor must be a floating point tensor. Scale. The scale to use for quantization. This is a tensor with the same number of elements as the number of channels in the input tensor. 0 point. The 0 point to use for quantization. This is a tensor with the same number of elements as the number of channels in the input tensor. D-type. The data type to use for the quantized tensor. This must be a quantized data type such as torch, quint8, torch, quint8, or torch, quint32. Axis. The axis along which to quantize. This defaults to -1, which means that each channel will be quantized individually. Outputs. Quantized tensor. The quantized tensor. This tensor will have the same shape as the input tensor, but its data type will be the specified quantized data type. Steps. The function first calculates the scale and 0 point for each channel based on the input tensor scale and 0 point values. Then, it converts each channel of the input tensor to the specified quantized data type, using the calculated scale and 0 point for that channel. Challenges and fixes. Challenge 1. Quantization can introduce noise, which can degrade the accuracy of a model. Sample use case that resulted in challenge 1: a model that is trained on floating point data and then quantized to UINT8 can experience a drop in accuracy due to quantization noise. Fixes to challenge 1: use a higher quantization resolution, such as QINT8 or QINT32, to reduce the amount of quantization noise. Use a post-training quantization technique, such as calibration, to minimize the impact of quantization noise. Challenge 2: quantization can lead to overflow issues, which can cause the model to output incorrect results. Sample use case that resulted in challenge 2: a model that uses large input values may experience overflow issues when quantized to a smaller data type, such as UINT8. Fixes to challenge 2: use a larger quantized data type, such as QINT32. To avoid overflow issues, use a technique called clamping to limit the values in the input tensor to a range that can be represented by the quantized data type. Challenge 3: quantization can affect the performance of a model, especially if it is not done correctly. Sample use case that resulted in challenge 3: a model that is not properly quantized may experience a significant drop in performance. Fixes to challenge 3: use a quantization scheme that is appropriate for the model's architecture and the data being processed. Carefully select the scale and 0-point values to minimize the impact of quantization on performance. Optimize the code to take advantage of the benefits of quantization. Torch dequantize. Description: the torch dequantize function in ptorch is used to convert a quantized tensor back to a floating point tensor. Quantization is a technique used to reduce the memory footprint and computational cost of models by representing values with lower precision. However, for operations requiring higher precision or compatibility with other libraries, dequantization is necessary. Inputs. Input 1: quantized tensor. The input tensor that needs to be dequantized. It must be a quantized tensor, typically created using functions like torch, quantizepertensor or torch, quantize per channel. This tensor contains the quantized values that represent the original data. Outputs. Output 1: floating point tensor. The output is a floating point tensor containing the dequantized values. It represents the original data in its full precision, similar to the tensor before quantization. Steps. Step 1: dequantization process. The dequantize function applies the inverse quantization process to the input tensor. It uses the scale and 0-point information associated with the quantized tensor to reconstruct the original floating point values. Challenges and fixes. Challenge 1: precision loss. While dequantization aims to restore the original data, there can be some precision loss due to the inherent limitations of quantization. Sample use case that resulted in challenge 1: applying dequantization after complex mathematical operations involving quantized tensors might result in slight precision differences compared to performing the operations on the original floating point tensors. Fixes to challenge 1: use higher precision quantization schemes, e.g., torch, QINT8 instead of torch, QINT8 to minimize precision loss during quantization. Avoid unnecessary dequantization and requantization steps to maintain precision. Challenge 2: compatibility issues. Dequantization is often necessary for operations or libraries that only support floating point tensors. Sample use case that resulted in challenge 2: integration with external libraries like NumPy or TensorFlow might require dequantization to handle data exchange correctly. Fixes to challenge 2: use libraries that support quantized tensors directly, such as ptorch quantized operators and functions. Convert the quantized tensors to NumPy arrays and then dequantize them using the NumPy float 32. D type.